Computing equilibria with the sequence form realization plans. In the sequence form, take the role of mixed strategies in the strategic form. In fact, the mixed strategies X and Y are a special case by letting E and F in 3.25 be single rows, 1 to the transpose, and E equals to F equals to 1. The computation of equilibria with the sequence form uses linear programming duality, which is also of interest for the strategic form. Consider a fixed realization plane Y of player 2. A best response X of player 1 is a realization plane that maximizes his expected payoff X transpose times AY. That is, X is a solution to the linear program LP. Maximize X transpose times AY subject to E times X equals to E and X is greater than equals to 0. This LP has a dual LP with a vector U of unconstrained variables whose dimension is 1 plus the size of H1, the number of rows of E. This dual LP states minimize E transpose times U subject to E transpose times U is greater than equals to A times Y. Both LPs have feasible solutions, so by the strong duality theorem of linear programming, they have the same optimal value. Consider now a zero-sum game where b equals to minus a. Player 2, when choosing y, has to assume that her opponent plays rationally and maximizes x transpose times a times y. This maximum payoff to player 1 is the optimal value of the LP, 3.27, which is equal to the optimal value E transpose times U of the dual LP 3.28. Player 2 is interested in minimizing E transpose times U by her choice of Y. The constraints of 3.28 are linear in U and Y even if Y is treated as a variable. So, a min-max realization plane Y of player 2, minimizing the maximum amount she has to pay, is a solution to the LP. Minimize E transpose times U for those pair UY subject to F times Y equals to F, and E transpose times U minus AY is greater than equals to 0, and Y is greater than equals to 0. The dual of this LP has variable V and X corresponding to the primal constraints Fy equals to F and E transpose times U minus AY is greater than equals to 0, respectively. It has the form maximize pairs of UV, maximize under the pairs of UV of the following F transpose times V subject to E times X equals to E, F transpose times V minus A transpose times X is less than equals to 0, and X is greater than equals to 0. It is easy to verify that this LP describes the problem of finding a max-min realization plane X with a max-min payoff F transpose times V for player 1. This implies first that any zero-sum game has an equilibrium XY. More importantly, given an extensive game, the number of non-zero entries in the sparse matrices E, F, A, and the number of variables is linear in the size of the game tree. Hence, we have shown the following. Theorem 3.13. The equilibria of a two-person zero-sum game in extensive form with perfect recall are the solutions to the LP 3.29 with sparse payoff matrix A, in 3.26 and constrained matrices E and F in 3.25, defined by proposition 3.10. The size of this LP is linear in the size of the game tree. A best response X of player 1 against the mixed strategy Y of player 2 is a solution to the LP 3.27. This is also useful for games that are not zero-sum. By strong duality, a feasible solution X is optimal if and only if there is a dual solution U fulfilling E transpose times U greater than equals to AY and X transpose times AY equals to E transpose times U. That is, X transpose times AY equals to E transpose times X transpose times E transpose times U, or equivalently, X transpose times the following term, E transpose times U minus AY equals to 0. Because the vectors X and E transpose times U minus AY are non-negative, 3.31 states that they are complementary in the sense that they cannot both have positive components in the same position. This characterization of an optimal primal dual pair of feasible solutions is known as complementary slackness in linear programming. For the strategic form, this condition is equivalent to the best response condition 3.2. For player 2, the realization plane Y is a best response to X if and only if it maximizes X transpose times B times Y subjected to F times Y equals to F, Y is greater than equals to 0. The dual of this LP has the vector V of variables and says minimize F transpose times B subjected to F transpose times B is greater than equals to B transpose times X. Here, the primal dual pair YV of feasible solutions is optimal if and only if analogous to 3.31. Y transpose times the following term, F transpose of V minus B transpose times X. The result is 0. Considering these conditions for both players, this shows the following. Theorem 3.14. Consider the two-person extensive game with sequence form payoff matrices A, B, and the constrained matrices E, F. Then the pair XY of realization planes defines an equilibrium if and only if there are vectors U, V, so that E times X equals to E, X is greater than equals to 0, F times Y equals to F, Y is greater than equals to 0, E transpose times U minus A, Y is greater than equals to 0, F transpose times V minus B transpose times X is greater than equals to 0, and 3.31, 3.32 hold. The size of the matrices E, F, A, B is linear in the size of the game tree. The conditions 3.33 define a linear complementarity problem, LCP, for a game in a strategic form. 3.8, 3.9, and 3.10 define also an LCP, to which the LH algorithm finds one solution. For a general extensive game, the LH algorithm cannot be applied to the LCP in theorem 3.14 because U and V are not scalar dual variables that are easily eliminated from the system. Instead, it is possible to use a variant called Lamke's algorithm. Similar to the LH algorithm, it introduces a degree of freedom to the system by considering an additional column for the linear equations and the corresponding variable z0, which is initially non-zero and which allows for an initial feasible solution where x equals to 0 and y equals to 0, then a binding inequality in R equals to E transpose times U minus AY is greater than or equals to 0, or S equals to F transpose times V minus B transpose times X is greater than or equals to 0, means that a basic slack variable, R rho or S tau, can leave the basis with X rho respectively Y tau entering while keeping 3.10. Like in the LH algorithm, this complementary pivoting rule continues until an equilibrium is found. Here, or when the auxiliary variables z0 leaves the basis.